Hello everyone, I'm Sundas Iftikhar, a PhD student at School of Electronic Engineering and Computer Science, Queen Mary University of London. Today I'm going to present our latest work, FogDLearner, a deep learning based cardiac health diagnosis framework using fog computing. It is accepted in Australian Symposium on Parallel and Distributed Computing. Agenda of my today's presentation is I'll start with introduction, then motivation and our contributions, existing solutions, critical analysis, problem statement, proposed model, performance evaluation, experimental results, and future work. Heart disease is considered as one of the major reasons of deaths. According to a report by World Health Organization, in 2019, an estimated 17.9 million people died of heart disease, which is about 32% of total global deaths. With the advancement in IoT infrastructure, now we can easily capture health parameters using IoT devices. But increased adoption of IoT devices has also increased data generation rate and volume. Transmission of huge volume of data from thousands of IoT devices is gradually making cloud insufficient for latency sensitive healthcare application. And when we talk about smart healthcare systems, latency and response time are very important factors. As reacting fast to a disease like heart attack can save many lives. But nowadays most of the healthcare systems are cloud based. The computing model of healthcare application must satisfy following 5 requirements. Low latency, as fast response time can reduce treatment cost and save patient life. Reduce usage of network resources because all healthcare data need not to send to the cloud. Accuracy and reliability of data. As accuracy of diagnosis all depend on accuracy of data, so data should be reliable. When we collect data from different devices, it can be noisy or it can be less integral. Accuracy of prediction is also a very significant factor, how well your model predicts a disease. And its computing model should also be capable of communicating heterogeneous devices because we are using different devices for collecting data. Motivation of this work is to design a heart disease diagnosis system which can respond in real time with reliable accuracy. Our contributions are: we propose a fog-based framework for disease diagnosis that explores the trade-off between accuracy of disease prediction and quality of service parameter for fog computing. We use a fog-based cardiac disease prediction case study and a deep learning model for cardiac disease prediction. We evaluated the proposed model on pure HSIM simulator in terms of latency, resource utilization, and energy efficiency. There are various healthcare frameworks that have been proposed and cited in literature. I will discuss some of them. For determining physical fitness of sedentary people, a healthcare framework is proposed and they use FogDLearner for pre-processing of data in their proposed model, and analysis is done on cloud. For analysis purpose, they use k-mean clustering, and dataset they use for this work is health, physical posture, behavior, and environmental data. Another healthcare framework was proposed for monitoring and control of mosquito-borne disease. And in their proposed work, they use FogDLearner for data analysis, clustering, and data sharing. The cloud layer is used for social network analysis to prevent extensive spread of mosquito-borne disease. But they ignored the parameters of standard systems such as latency, quality of service needs, and energy consumption. In another work, a heart disease prediction system is proposed, and for prediction of disease, they use ensemble deep learning. In ensemble voting or learning, it requires to train a large number of neural networks, so they require much more bandwidth and energy than normal systems. Another system is proposed for monitoring diabetic patient nutritional intake and physical activity to manage blood glucose level. For accurate prediction of blood glucose risk level, they use J48 graph decision tree, and they did their evaluation using a case study on smartphones. A cloud-based heterogeneous Internet of Healthcare Things communication framework is proposed, and in their proposed work, they use 5 layers: perception layer, mist layer, fog layer, cloud layer, and application layer. But the focus of their work was to stream the data and transmission of the data, not on processing and analysis of data. They only focus on controlling end-to-end latency and packet drop rate. Table 1 compares our work with the other works of the literature. The parameters we use for comparing our work with existing healthcare models are fog-based mechanism they use for prediction, disease for which they propose the framework, power, network usage, execution time, mobility, and implementation of the work. Problem statement of our case: in application scenario of diagnosing a cardiac disease, there is a need to process the data close to the body with high prediction accuracy and low energy consumption. This is our proposed framework. It considers the accuracy of prediction as well as quality of service parameters of healthcare applications. Figure 1 shows the architecture of our proposed framework, and it also shows the flow of data between different modules. Our proposed framework consists of 3 layers: IoT layer, fog layer, and cloud layer. IoT layer collects 2 types of data, that is physiological data and electronic medical record. For collection of physiological data, we use 3 types of sensors: medical sensor, environment sensor, and activity sensor. The parameters we captured using these sensors are EEG, EMG, ECG, heart rate, body temperature, oxygen saturation, glucose level, respiration rate, and blood level. Gateway device collect all this data from the IoT layer and send it to fog layer. Broker node at the fog layer receive this data and analyze the availability index of fog compute node and fog storage node and assign tasks to them. Broker node have 2 parts: prediction engine and cloud integrator. Prediction engine receives data and tasks from gateway device, and it checks the availability index of the for compute node and for storage node, and also analyze the data that is sent for the prediction. If the availability index of the compute node and for storage node is less than a specific threshold, then it will send the data to the router. Otherwise, it will send data to the cloud integrator. Router is an intermediate device that will send data to the fog compute node or fog storage node. Fog compute node is a device that has already trained recurrent neural network on it. It will receive the data that is sent for processing and analysis. It will process it and give its prediction results. Fog storage node is used to store data at the fog layer. Cloud integrator, on receiving the data and tasks from the prediction engine, it sends the data and tasks to the cloud layer. Cloud layer have 2 nodes: storage node and compute node. The task received at the compute node, and it will process and analyze the data and predict the result whether a patient has heart disease or not. Cloud storage node is used to store the data. This is the operating mechanism of our proposed framework. Physiological data and electronic medical record is entered as input, and it gives the output whether a patient has heart disease or not. Data is collected and by gateway device, and this device sends it to the broker node. At fog layer, availability index is checked. If availability index is less than a threshold, then it will send data and tasks to the fog worker for processing, as it will send data to cloud layer for processing, and both of them will return the results. It works in master workers manner. We use 2-class recurrent neural network for prediction. reason because we use these two-class neural network is that it guarantees a good trade-off between training and time and performance. Now I will discuss the experimental setup. The dataset we use to train our classifier is from heart patient dataset from UCI machine learning repository, and the output indicates are 1 and 0. 1 shows have heart disease and 0 otherwise. Table 2 shows the attributes we have in our dataset. We use 14 attributes, and a description and possible values of these attributes is given in table 2. The parameters we employed for training our classifier are given in table 4. We have set number of hidden nodes to 100, learning rate to 0.1, number of learning iterations to 100, and the normalizer we use is min-max normalizer. We evaluated our FogDLearner using pure HSIM simulator. The experimental setup for our simulation include 1 cloud server, 4 Fog data centers, 4 Fog devices, 2 moving devices, and 2 fixed devices. Basically, we have divided our devices into 2 equal parts. One part is set as moving devices and one part is set as fixed devices. The parameters of moving and fixed devices is given in table 5. Now I will discuss the result of our classifier and our simulation. Figure 2 shows the training and testing set ROC curve, and as we can see, it shows a good true positive rate for prediction. And our classifier has 94.9% AUC. As we know that closer the value of AUC to 1 shows a good performance of the classifier. So our performance of our classifier is relatively good, 94.9%. These are the results of our simulation. We have evaluated our FogDLearner in terms of execution time, network usage, energy consumption, and CPU utilization in underload and overload scenarios. Figure 4 shows the execution time for different number of workloads as number of devices. We observed a linear scaling in execution time for both Fog and the cloud, but simply shifting to a higher value in case of cloud. Execution time of the task at the cloud is very low, but when we include the transmission time from device to the cloud, then total execution time increases. Figure 5 shows the comparison of network usage for FogDLearner and cloud-only approach. We also observe here the linear scaling of the network usage with number of devices. But here we can see that the FogDLearner approach scales better in this scenario, as in FogDLearner the execution of data is done near the devices. That's why the network usage is less than the cloud in FogDLearner. Figure 6 shows the comparison of energy consumption, and energy consumption is also observed as the increase linearly. As we increase the number of devices, energy consumption also increases. Figure 7a and 7b compare CPU utilization using FogDLearner and cloud-only approach for underload and overload scenarios. We observe that in an overload scenario, CPU utilization reaches to 100% faster in case of Fog approach, while cloud scales better in overload scenario. We also observed that the Fog reached to 100% CPU utilization faster in overload scenario as well, as we expected. Conclusion and future work. We propose a framework called FogDLearner, conducted experiments using use case related to cardiac health diagnosis, compared the advocacy and performance of FogDLearner using pure HSIM simulator. There are different directions that we can follow for future work. One can be conservation of energy of edge devices. That is a big challenge nowadays, And other direction can be FogDLearner should incorporate dynamic scalability to analyze execution time scale with number of devices.